question says that the graph shown has 8 edges with distinct integer edge weights. The MST, that means the minimum spanning tree, is of weight 36 and contains the edges AC, BC, BE, EF and DF. The edge weights of only those edges which are in the MST are given. The minimum possible number of weights of all 8 edges of this graph is. Okay, so you are given the weight of those edges that are present or that are a part of the minimum spanning tree, but the remaining edges like ED, CD and AB are not given, or their weights are not given, and you have to tell what is the minimum possible sum of the weights of all the combined edges. So we know that the current weight of the MST, or the sum of the edges in the MST, is 36, and if we find the weight of AB, CD and ED, then we'll get our answer. Alright, so one thing you need to remember, that a MST, a minimum spanning tree, has all those edges that do not form a cycle and that are minimum weight edges that connect a vertex that is not present in the set of vertices that are already included in the MST. Alright, so if we look at this A, B and C cycle, then we see that in the MST which edges are included? AC and CB. The edge AB is not included. This ABC forms a cycle, and if we are not including one edge from this cycle, it means that this edge must have been the highest weight edge, because we need all the vertices in the MST, and therefore we would need A as well as B as well as C, and the minimum number of edges that would be required to connect 3 vertices to other vertices of this graph would be two edges. Okay, so we would have to choose any 2 edges between AB, AC and BC, and since it is a minimum spanning tree, we would choose the minimum weighted edge. Okay, and the 2 edges that are selected are AC and CB, therefore these would have been the minimum weighted edge. Thus we can without any doubt, or we can clearly say that the weight of AB must have been greater than the weight of the highest or the maximum weight edge out of AC and CB. Okay, so weight of AB must have been greater than the max of the weight of AC and the weight of BC. Alright, and what is the max out of 2? The max out of 2 is 9. Therefore, we can say the weight of AB must have been greater than 9, or we can simply assume it to be 10. And why we have assumed it to be 10 and no other value? Because we have found, or we have to find, the minimum possible sum of weights of all these edges. So the minimum weight that is greater than 10 would be the minimum weight that is greater than 9 would be 10. Okay, now similarly, if I consider this cycle, the cycle E, F and D, we can simply, or we would write the same the same for this cycle also, that the weight of the unweighted edge ED would be greater than the max of the 2 edges that are given, 4, 4 and 6. 4 is the weight of EF and 6 is the weight of DF. Okay, so if these are the edges that are minimum out of the 3 edges ED, DF and EF, then definitely weight of ED would have been greater than the max of the 2, which means this weight would have been greater than 6. Thus we can say weight of ED would have been 7, or we can safely assume the weight of ED to be 7. And on similar grounds, if we have said that this is 15, this is 2 and this is the edge ED, we have assumed it to be 7, then CD would have been greater than 15. Okay, So because 15 is an edge that is chosen over the edge CD. Thus, this edge CD would even weigh more than the edge that has been selected in the minimum spanning tree. Alright, so we can assume that the weight of CD must have been greater than 15, and therefore we are assuming it to be 16. Alright, so the sum of all the edges would be the sum of the edges that are present in the minimum spanning tree, that counts, or the sum is equal to 36 plus 10 plus 7 plus 16. Alright, so this would give you a total of 36 plus 33, and that comes out to be 69. Alright, so that's how you'll calculate what can be the minimum possible sum of weight of all the 8 edges of this graph. Alright, and you can write this answer here because it's a numerical type of question. Now coming to the second question of this lecture, the question states that let G be a connected planar graph with 10 vertices. If the number of edges on each face is 3, then the number of edges in G is. Alright, this is also a question from GATE 2015, and you have to remember certain formulas for this question to be solved very quickly. See, you know that by Euler's formula you can say that by Euler's formula we know that the equation V minus E plus F is equal to 2. And what does VEF stand here? V stands for vertices, E stands for edges, and F stands for faces. Alright, so since you are given that the number of vertices are 10, alright, and you are also given that the number of edges on each face is 3. Number of edges on each face is equal to 3. Now, apart from this relation, you must remember that every edge is shared by 2 faces in a connected planar graph. Okay, I'll write it down for you that every edge is shared between, or it is shared by 2 faces in a connected planar graph that is given to you. Therefore, by the above 2 lines, you can safely assume the relation twice the number of edges is equal to thrice the number of faces. Okay, because each edge is shared by 2 faces, and each edge, the number of edges on each face is 3. Alright, so this is relation number 1. This is the second relation that we have obtained, or that we actually can derive and know. And now if we equate both these relations, we'll get the desired answer. We have to find the number of edges. So if I write f from 2, I can write f as 2e by 3. Alright, and if now I put this equation in 1, this is equation 3, and if I put 3 in 1, I'll safely get the value v is 10 minus e plus f is 2e by 3 equal to 2. Alright, so this is equal to 10 minus 3e plus 2e by 3 equal to 2. This is equal to 30 minus e equal to 6, and e is equal to 24. Alright, so e equal to 24 is your answer, or there are 24 edges in a connected planar graph which has 10 vertices, and the number of edges on each face is 3. Okay, so that is how you will solve these 2 questions. These were not very difficult questions, but yes, you need to understand the basics of each concept that is taught to you in such type of subjects like data structures, you have to know the concept behind a minimum spanning tree and the faces and the relation between the edges. With our first question, a binary tree T has 20 leaves. The number of nodes in T having two children is. Alright, so one thing you must remember, one of the major formula in binary trees is that sum of the degree of all nodes is equal to twice the number of edges. So I'll write it down. Sum of the degrees of all nodes is equal to twice the number of the edges that are present in the tree. Alright, so what different kind of nodes do we have? We have leaves in a tree, we have internal nodes in a tree, and we have two kinds of internal nodes. Root is an internal node that does not have an incoming degree, while there are all other internal nodes have an incoming degree as well as an outgoing degree. Okay, incoming degree means there is no edge that ends at root. Okay, so we have basically three types of nodes that we can say. So the sum of the degree of leaves plus summation of the degree of internal nodes except the root. Alright, and here this is except the root, and the sum of the degree of the root, this will all contribute towards twice the number of edges, since the number of edges in any tree is equal to the number of nodes minus 1. Okay, so if we have two nodes in a tree, then the number of edges would be 1. If there are 3 nodes, then the number of edges in the tree would be 2. So we can say that the right hand side, twice the number of edges, can also be written as twice nodes, the number of nodes minus 1. Alright, so if I denote the degree of leaves as L, the internal nodes as I, the root as, or if I say assuming it to be a k-ary tree, or instead of a binary tree, I'm assuming the degree of the tree to be k. Alright, since each internal node has k children, and as well as it has an incoming degree from its parent, therefore the degree of each internal node would be k plus 1. But for the root, the degree would be k because it does not have an incoming node, because root, it does not have any parent. That is why we wrote the root separately. So if L is denoting leaves, since the degree of each leaf is 1, only the incoming degree from the parent, therefore I'll write L into 1. L denotes the number of leaves, I denotes the total number of nodes, but since we are subtracting root from it, therefore I write I minus 1. K is the degree of each internal node plus 1 for its incoming degree, alright, from the parent, and there is a single root, the degree of that root is k, alright, which is equal to twice the number of nodes. Total number of nodes are number of leaves plus total number of internal nodes, alright, and minus 1 from here. So this is the equation that we get. This is a general equation. Now we are not particularly specifying for a binary tree. Currently I have assumed the value of k as anonymous, okay, or I have not taken any particular value of the degree of a tree. It is k only. Let's solve this question or this equation to a simpler version, and then we'll substitute the values. So this comes out to be L plus ki minus k plus I minus 1 plus k equal to 2L plus 2I minus 2. Alright, now minus k plus k get cancelled. What we are left is L plus ki plus I minus 1 is equal to 2L plus 2I minus 2. Alright, so reducing it further, if we take L on one side and the remaining values on the other side, you'll be left with 2L equal to Ki plus 1 minus I, or you can say K minus 1 I plus 1 is equal to L. Now we know that K is equal to 2 because it's a binary tree. K is the degree that we assumed. Okay, you are given L as 20. Alright, so you have to find the number of internal nodes with 2 children. So K is 2, 2 minus 1 is 1. 1 into I plus 1 is equal to 20. Therefore, what you get? You get I equal to 20 minus 1 as 19. Alright. This was one way of solving this question when you are given the number of leaves and you have to find out the number of nodes in the tree having 2 children. Now there is another similar question that appeared in the same year of GATE 2015 but in different set. Okay, there are two different sets of GATE paper, and in the second set the same type of question appeared but in with different values. So the second question that we solve is, consider a binary tree T that has 200 leaf nodes, then the number of nodes in T that have exactly 2 children. So I'll solve this question with another way so that if you do not clearly understand this way or this method, you will be able to grasp the second one. So in this question, let's assume that nodes that have exactly, okay, I'm writing in the short form, that nodes with exactly 2 children, I'm taking the number of such nodes as x, then nodes with exactly one child, I'm taking the number of such nodes as y. Okay, now what would be the total degree? The total degree would be the degree of the leaves. How many leaves you are given? There are 200 leaves and each has a degree of 1. So 200 plus 3 of x. Why 3 of x? Because each node that has 2 children, each internal node would have 2 outgoing degree, that means 2 children, as well as 1 incoming degree from its parent. Therefore 3x plus, similarly, each node with a single child has an outgoing degree and an incoming degree. Therefore 2y minus 1. Why minus 1? Because in the nodes that have 2 children, we have included all the internal nodes, but root is one internal node that does not have degree 3. It has degree 2. Therefore, we'll subtract 1 for the incoming degree of root, which does not exist. Okay, so in 3x we included all internal nodes, but we would subtract 1 because root is an internal node that does not have any incoming degree. Alright, so what would be the total number of nodes here? Total number of nodes would be x plus y, number of nodes with 2 children plus number of nodes with 1 child plus the total number of leaves. That means the number of nodes with no children. Also, what would be the total number of edges? Total number of edges, you can write them as the total degree divided by 2. Just like we saw here that sum of the degree of all nodes is equal to twice the number of edges. So taking 2 on the other side, you can write this in equality as total degree of all the vertices divided by 2. Now what is a total degree? What is the total degree in this case? The degree of the leaves, which is 200 plus 3x plus 2y minus 1 divided by 2, and this is equal to the number of nodes minus 1. Alright, so what would be the equation that would come up? 200 plus 3x plus 2y minus 1 is equal to twice into the number of nodes minus 1. Total number of nodes are x plus y plus 200 minus 1. Alright, so if you solve this further, 3x plus 2y minus 1 is equal to 2x plus 2y plus 400 minus 2. So solving further, you will finally get an answer of x equal to 199. X was the total number of nodes that have exactly 2 children. Okay, now both these questions are very good for understanding the total concept behind the relation between the number of leaves, the edges and the nodes, and the degree of all such vertices or nodes. But in case of papers like GATE or UGC, sometimes you are running short of time and you need to know simple tricks that will help you to find out the answers quickly as well as correctly. So in such type of questions, one major formula that you can safely assume is that if you are given the total number of leaves and you have to find out, in case of a binary tree, then the number of nodes having 2 children you have to find out, you can safely assume the answer to be the total number of leaves minus 1. That means in this question, the number of nodes having 2 children would be total number of leaves, that is 20 minus 1, which is 19. Here also the total number of leaves are 200. 200 minus 1 is 199. That is how we achieved it. So I wanted to explain you how this shortcut appeared and why this shortcut holds true. So if you are able to remember this, well and good. Otherwise, you need to remember certain formulas that I have written here. Firstly, the sum of the degrees of the two vertices of all the vertices of a tree is equal to twice the number of edges. Then you need to also remember that in a tree, the number of edges is also equal to the number of nodes minus 1. Alright, so such small formulas would help you in solving complete questions together as a whole. So that's all for today's lecture. If you understood these questions, please like our video and give your feedback in the comment section below. Subscribe to the channel of Easy Engineering Classes for more such tutorials on various computer science related subjects as well as our preparation series. Press the bell icon to get the notifications of our upcoming videos. Stay tuned to our channel. Good luck for your exams. Thank you.